Okay, let's get started. There once was a time when no one worried about vibration. Equipment like that, if it broke, they could cast a heavier part. It weighed maybe another ton, and that gave them better traction. So eventually we got away from steam and went to diesel. We didn't have to stop for watering. Much higher velocities, much better ratio of force to mass as locomotives went to diesel electrics. Here we see a test lab. People are simulating on rolling equipment what that rolling equipment would eventually experience on the track. But the real interest in vibration came with the air age. Aircraft vibrations are very definitely of concern. This next airplane that I'm going to show you first flew about 1952, and 744 of them were built. 76 of them are still flying, and those were built about 1966. And my first vibration experience was on B-52 aircraft, full-scale models of that aircraft. We were doing what are called modal tests that we're going to discuss later. The main purpose of that kind of a test was to experimentally verify the natural frequencies that the designers had predicted. Their concern was flutter. They wanted to avoid in-flight flutter. There is currently concern about the switch of aircraft construction from metals to plastics. And here is an animation of a particular mode, greatly exaggerated. You'll never see anything like this on a real aircraft. The only mode you're likely to ever see as a passenger might be looking out at the wing tips and seeing them move a little bit relative to the body. So this is hugely exaggerated, one of many modes that we're going to look at over the next few hours. Have any of you ever flown in a helicopter? You've experienced vibration. They definitely shake. The main source is the main rotor blades passing over the cabin. Two rotors, more vibration. Any propeller-driven vehicle, aircraft or ship, is going to generate vibration. And that vibration is something we don't particularly want. It becomes sound, travels through the water, gives away our location, our identity, our speed, and so forth. Especially we're concerned about that if we're the crew of a submarine and the enemy has lowered a sensor to listen to us and identify us. In those circumstances, we want to reduce vibration if we can. Vibrations are measured with accelerometers, which we didn't have at the time I got into this vibration business. I want to say just a few words about climatic environmental testing. It wasn't necessary to take this vehicle to the North Pole to find out if it would survive. Instead, they put it into a chamber and pulled the temperature way down. And that sort of climatic environmental testing is done on equipment. Our focus, however, is going to be on dynamic environmental testing, vibration and shock. Let's imagine that we're in the chase plane looking back at this aircraft. We can't see the mechanism that generates vibration. It's airflow, high velocity airflow over all the skin surfaces, causing that surface to vibrate locally. And that vibration is transmitted structurally and acoustically throughout the entire vehicle. Everything on board vibrates. This is of particular interest to the electronic circuit cards, which we're causing to vibrate, possibly damage them. This strike fighter, I presume, vibrates more severely in flight than did the aircraft that we saw a few moments ago, because there's more hardware out in the airstream being vibrated. The most severe vibration is at rocket liftoff, when rocket engines are firing. Hardware on board that vehicle are getting vibrated severely, and that vibration has to be reproduced in the lab for experimental purposes to find out if the hardware will survive. At one time, 2 or 3 pieces of hardware were built, one or two for testing and one for flight. But in recent years, in an effort toward economy, they sometimes only build one. And they hand that one piece of hardware to the lab and say, here, test it. But don't break it because we have to fly it next week. Well, that inhibits our testing somewhat. Hardware that goes to the military is often used in very strenuous circumstances. It has to be rugged to withstand this kind of an environment. And our hardware, I think you can imagine, can find many ways to fail. And we're going to identify those. One of the sources of vibration on that vehicle might be gear trains. Each gear turning at a particular speed, and the frequency of that gear's contribution is that RPM multiplied by the number of teeth on the gear. Some propulsion machine, some sort of an engine firing is going to create vibration felt throughout the vehicle. Have any of you experienced wind-induced vibration? If you happen to have a sailboat, then you definitely have felt vibration of the hull and the rigging and the sails themselves. I mentioned wind-induced vibration because in September 1940, near Tacoma, Washington, the Tacoma Narrows Bridge experienced damaging vibration. And this video that's coming up here is a classic that civil and structural engineers all study. There we see a distance shot of that bridge flexing in the wind. It took several hours of a steady wind blowing to come up to that intensity of response. Definite resonant behavior. I'm guessing, Brett and my audience, that you have some interest in the drilling into the earth, drilling for oil, drilling for water. Well, that drilling action, especially through rock, creates vibration. And in certain instances where the smart drill bit is sending information up to the surface, that vibration can be detrimental to that smart drill bit. So drill bits are vibration tested. Another form of vibration is seismic, earthquakes. And a very damaging earthquake took place in the Northridge area of Los Angeles in January 1994. Here another earthquake is just getting started, and the rocks are coming tumbling down off the hill. A few minutes ago, they seemed to be very firmly attached, but now they're tumbling. The attachment didn't hold up. This is Interstate Highway 5 near Los Angeles, the bridge over that interstate. And interestingly, the previous bridge had failed at the same location in an earlier earthquake. We're not real sure about the bridge that's there now. Will it survive an earthquake? We don't know for sure until that happens. But there are some seismic vibration tests that are done on equipment to reassure ourselves that our equipment will survive. We're not sure whether this equipment will survive the next earthquake or not until that earthquake happens. But failures do take place, and we are going to talk about seismic vibration testing. I imagine that each of you has experimented with a paper clip, has bent it back and forth and counted the number of cycles to failure. And then conceivably, you made a stress riser in the wire on another paper clip. And it took fewer cycles to get a failure. Those paperclip fatigue failures were rather trivial compared to some de Havilland aircraft that took off from Rome in 1953. One, and then another one from Rome. And in these, the debris was scattered. But a third one took place, and they were able to find the tail and the fuselage underwater. And they discovered that the cabin had exploded. Now, de Havilland designers had worried about cabin pressurization. They were designed for maybe 20 pounds per square inch. And the labs had performed static tests out to 16.5 psi on every aircraft. But after those 3 disasters, then they did some cyclic pressure tests, and they found a corner of a cabin window cracked, and the crack spread rapidly. And that failure led to reinforcing that area on future aircraft, starting with Comet 4. And more recently, but not the last such failure, Aloha Flight 243 in Hawaii came apart in flight. The cabin peeled off. Fortunately, the pilot was able to land the aircraft, as you see here. They only lost 1 crew member in that experience. That aircraft had had over 75,000 pressure cycles, takeoffs and landings, very short flights among the islands in Hawaii. And the investigators looking at that aircraft found corrosion. They found epoxy had debonded. These troubles hadn't been seen by maintenance personnel working at night with flashlights. But this led to improved bonding and improved inspections. Currently, a number of aircraft are wearing out and should be replaced. Let's change the subject and talk about electrical connectors. They're supposed to be zero resistance, 100% conductivity, and they are, but under vibration sometimes they open momentarily, and that opening can badly affect downstream electronics. So we are concerned about those, and we do vibration tests on connectors using a shaker and electronics monitoring of circuitry. We've found that these USB connectors are very intermittent. We have military type connectors that can stand up under vibration inputs. So there are standards for such tests, and there are electronic devices for monitoring the contacts to make sure that they don't open. If they do open, it is recorded. Well, what is vibration? It's kind of hard to describe, but referring to your gymnasium and machinery like that, almost everybody understands what you're talking about. Webster gives us a definition, one line of which is useful, one line of which applies to our discussion here. This periodic motion of the particles of a plastic body and so forth. That's a good definition for some of our work. That definition is okay when we're talking about sinusoidal vibration, but it doesn't fit when we're talking about random vibration, an important subject these few hours together. Let's imagine that this automobile in which we're riding has been instrumented. 3 accelerometers have been placed on the suspension, and they're recording vibration as we go along. What do those records look like? We'll examine them in a minute. But part of the vibration that they're recording is from the engine and the drivetrain. That dictionary definition that we saw applies to this contribution, but it doesn't apply very well to the road inputs. Another use for measuring vibration is diagnosing difficulties inside machines. The vibration signature changes when some part wears or breaks. And this technician is comparing today's spectrum with a spectrum taken when the machine was new to predict what has gone wrong inside the machine. That dictionary definition that we saw applies to this vibration very well. Machinery in your factory is probably isolated from the building so that the machine's vibration doesn't affect the building or the building's vibration doesn't affect the machine. So we are going to talk about vibration isolation under machinery. Vibration sometimes affects human operators. Gripping a machine tool can be damaging to the fingers and the hands and the forearms, especially if we're doing this in a cold situation. That's why the operator is wearing gloves to keep his hands warm, and those probably are cushioned gloves to protect his hand from the tool's vibration. That vibration can damage immediately and can lead to poor circulation and eventually gangrene and need for amputation. Remember this, please, later when we're talking about shakers at NIOSH, National Institutes for Occupational Safety and Health. They are concerned about hand-arm vibration. Let's go back and talk a little bit more about machinery vibration, the measurement and analysis. A vibration spectrum is a good way to describe complex vibration, vibration that simultaneously exists at several frequencies. Changes in that spectrum are what the investigator is looking for. And we'll talk about this considerably more in Lecture 11. But let's consider a possible spectrum. The vibration, as you can see, is focused on about 15, 30, and perhaps 56 hertz. There's a severe vibration at those three frequencies. There's also vibration at other specific frequencies, but those are down in the noise region, and they are very hard to measure. How could we get them to be bigger and easier to measure without driving the big contributors clear off the page? Well, instead of using linear scaling, 0, 5, 10, 15 inches per second, let's use logarithmic scaling. So now we're looking at logarithmic scaling of velocity. The big ones haven't gone off scale, but the small ones are larger and can be measured. And we are going to talk about logarithmic scaling. This dB scaling got started with the sound power measurements in telephony. And it's useful in vibration because we have small quantities and large quantities that we have to measure. Primarily, we're talking about power, the top line, and ratios between different power measurements, the second line. And the number of dB, well, before dB, investigators talked about the Bell, named in honor of Alexander Graham Bell. And the number of bells is really the exponent up here on the power line. And it turned out that the Bell is too large a unit. It's impractically large. And so the investigators cut the bells into 10 parts and started talking about decibels. Let's start here at unity, 10 to the 0 power, 0 dB. The original classic relationship here in decibel scaling is coming up. Please write this down somewhere. The number of decibels is equal to 10 times the log to the base 10 of a power ratio, some new power value being compared with an original power value. Now, power is proportional to voltage squared, and therefore we can, wait a minute, Wayne, back up here. Maybe not everyone in the audience agrees with this blue statement. Perhaps we'd better run an experiment. Make sure that everyone understands that power is proportional to voltage squared. Let's apply 1 volt to a 1 ohm resistor and have a current of 1 amp. And the power in that situation, I hope you said 1 watt, but then let's double the voltage and push 2 amperes through that resistor. And the new power value, I hope you're calculating, to be 4 watts. And that proves to us that power is proportional to voltage squared. So we take that original equation and modify it for situations where we're measuring voltage, and we square that voltage, or we can say that the number of dB is 20 times the voltage ratio. You're going to use whichever one of these equations fits, depending upon whether you're making power measurements or voltage measurements. In any event, you're going to pay attention to the original quantity. I call that P0 or E0. And we're going to compare new values with those classical values. Sometime when you were in school, I'll bet you saw a chart, something like this, with a number of decibels down the center, and 2 adjacent columns with power ratios, and the outside columns voltage ratios. A moment ago, we talked about doubling the voltage, quadrupling the power. And that situation is called an increase of 6 dB. And we talk about quartering or halving a voltage or a current. as a negative 6 dB. I presume that this is somewhat familiar to everybody. A little story in Sound and Vibration magazine a few years ago likened this to doubling your money, from 1 cent to 2 cents, from $1 to $2, and so forth. Those dimensions on this scale could be called 6 dB. The face value changes, but they're all the same thickness. So doubling your money on the upper scale, each of these arrows could be labeled 6 dB. I have a voltmeter at home. On the scale, a distance of 6 dB measures a doubling of voltage. Decibel scaling certainly is used in acoustics work, but we're going to find it useful in vibration work also, because we go from such a small fraction of a G sometimes to thousands of G intensity of vibration. And decibel scaling is very useful. What about shock measurements and shock testing? Well, let's talk about those also, but let's put them off to about lecture 28. Your slice of the world of vibration may be this little bit here, but I think you'll be a little bit interested in some of the other activities in the world of vibration, and we're going to talk about a few. I've drawn a horizontal scale here, scanning from 1600 to the year 2000, and I'd like to comment that there was some interest back in the 1600s. A few people were investigating vibration and writing down their thoughts, and they thought very logically, but almost everything of note has happened in the last 50 years or so, since we began measuring vibration on aircraft and other vehicles. In about lecture 28, we're going to talk about automotive testing. And that sled there, the dummy occupant, is going to behave very much the same under test, being yanked backward severely, as if he came forward and stopped abruptly. Now, ERI, Equipment Reliability Institute, exists because very few universities have practical vibration courses. Very few of them have shakers. Very few of them have shock test machines, accelerometers, strain gauges, and so forth. One of the few is California Polytechnic State University, Cal Poly at San Luis Obispo, California. A couple of pictures taken at Cal Poly, where students are very fortunate. They have an opportunity to get their hands on shakers and equipment. A design engineer in a course I was teaching on site, perhaps there were 14 designers and 4 lab people, and he said to me in class something like, "Lab details don't concern me." And I kind of jumped on him, because I think lab details do concern designers. They should be going to the lab and witnessing their own tests and asking questions about what's happening. Okay, and now a little video clip, a practical example of reliability.
Stand by!